Okay, so here we go. Well, welcome back. I'm glad you're here. And we finished last time Unit 3, dealing with soil acidity and alkalinity. And we're going to move into Unit 4 today. And this is either going to be a refresher or, um, building upon what you learned when you took introductory soil science, either last semester or several semesters ago, or even years ago. But we And I said this before, I've been thinking about removing this section from the class, and then I hesitate because when we talk about CEC and base saturation or cation exchange capacity specifically, cation exchange capacity drives the holding of not all, but most of the nutrients that are necessary for plant growth. And so you really need to understand what cation exchange capacity is and how it works, how it's formed, in order to understand some of the basics behind soil fertility. So this is a refresher for hopefully all of you. There's 6 learning objectives. The first one is you should be able to define cation exchange capacity. I'll give you a definition, but there's like 100 different definitions out there, but you should be able to define it. And then, of course, if you remember this, cation exchange capacity is driven by clays and organic matter in soils. And so objective number 2 is to understand the basic clay mineralogy that's present in soils across the globe, and specifically a term called isomorphic substitution as a source for cation exchange capacity. And you've probably heard isomorphic substitution before. And then objective number 3 is to understand the relative differences in cation exchange capacity among 1-to-1 and 2-to-1 type clays. So we'll talk about what those mean. And the cation exchange capacity from organic material or organic matter. And then you should be able to explain how pH affects cation exchange capacity in soils. So you'll learn about that in this unit. And then we're going to go back and touch on this concept of equivalence or equivalent weights. And so you should understand, have a general understanding of the meaning of equivalence as a unit of charge or charge density, and be able to calculate equivalent weight of different cations. We'll show you how to do that because that ties in directly with cation exchange capacity and how we determine cation exchange capacity in soils. And then, of course, that leads into actually being able to calculate cation exchange capacity and base saturation. So this unit somewhat ties back to the previous unit where we talked about base saturation. Then I'm going to show you some examples of how this works in the real world. And then objective number 6 is it says memorize. You're not going to have to do that unless you really want to, because for the exam, it's open book, open note. So you should know the lyotropic series. This is basically how different cations with different charges are sorbed onto clays or organic matter. But know the lyotropic series and understand how it affects cation exchange reactions. So we'll talk about that at the very end of this unit, okay? So let's move into cation exchange capacity. What is it? So I put together a relatively general definition, and you can look up a more complex definition if you want. And if you're given this question on an exam, what's the definition of cation exchange capacity? Feel free to put down whatever definition you find, as long as it's cation exchange capacity definition. This is really general in terms of how I would define cation exchange capacity. It's the quantity of positive charges that a soil can hold. And so when we talk about positive charges in soils, we talk about cations, right? So ions off the periodic table or from the periodic table that are positively charged. And so these are the cations that are, quote, stuck on the soil, and they're able to exchange with cations in the soil solution. And so these cations that are stuck on, we'll just keep it simple for now, that are stuck on the outside of soil particles or organic matter can move between being stuck and into the soil solution simply because other ions or cations exchange with the cations that are stuck on the soil, right? And you've probably learned about this before. If you haven't, not you. You should have all learned about this before. Okay, so CEC is really important. So what this tells you is one thing. It tells you one thing that's really important. And if you look at what I wrote here, the quantity of positive charges that a soil can hold. So if the soil can hold positive charges, that means that the soil itself is negatively charged, right? And you've probably learned this, that soils are negatively charged for a number of reasons. And you're going to learn about that today. So with that in mind, where does cation exchange capacity come from? So let's keep this simple. I'm going to throw you a question here based on these three pictures. So here are three pictures of sand, silt, and actually two different types of clays, a kaolinite and an illite or an illite smectite. And if you look at these three fractions of soil, you've learned about that, right? You've learned about this fractionation of soils for soil texture. You separate the sands, you separate the silts, and you can separate the clays, and then you come up with soil texture. But if you look at these three fractions, where does cation exchange capacity come from? From sands, silts, or clays? And why? Feel free to unmute. Yeah,
Are you looking for an answer?
I am.
Well, CC comes from the clay sites.
Yeah, how come?
I think it's because of how they layer out and they're like 2 to 1s. There's something with the structural chemistry of it.
Yep, we're going to talk about exactly that. Let's let's take a simpler approach and just look at what you see on the screen in front of you. And we touched on a really basic concept in soils before about surface area, right? And so typically the greater the surface area, the greater reactivity in soils. And so if you look at sand-sized particles, these are pretty big particles, and the surface area is relatively low because they're large. And even silts to some degree are actually pretty large. But if you look at clays, they just have like kaolinite has a lot of surface area. You can see all these little cracks or separations in the kaolinite itself that increases surface area for reactivity to occur. And then this is a horrible picture of this illite smectite, but this is also a clay and it looks amorphous, but it's actually crystalline, but it looks like a blob and it has a lot of surface area. And so when we talk about where does CEC come from, it actually comes from soil. There's very little CEC on sands. There's a little bit more in silts, but there is a lot of CEC derived from clay size fractions in soils because of surface area, right? So this ties back to some of the concepts we already talked about, like in the last unit when we talked about liming. And if you took a chunk of lime the size of my head and put it on a soil, it's just going to sit there and do nothing. So like my head is like a piece of sand, and it's not going to do anything in terms of improving CEC in this case, right? So almost all of the actions and interactions with CEC, not all of them, but almost all of them come from the clay that's present in the soil, and you're going to learn also organic matter in soil. So when you look at clays are made of building blocks. All clays are made of building blocks. And in fact, we now have techniques to actually identify how these actually look in the real world. Right. So when this was first, I don't know how they first discovered this. I should know this, but we have some techniques, some high-powered techniques to actually look at, for example, in this picture, how silicon binds with oxygen and how many oxygen atoms are around it. And so when we look at the building blocks for clays, there's two basic building blocks that comprise all clays. And the first building block is something called the silica tetrahedron. And tetra means four-sided. Maybe you can see that in this picture. There's there's um, there's a side on the bottom. There's a side facing you. There's a side back to the left and a side back to the right. It doesn't look quite like a pyramid, but it's almost like a pyramid, except instead of having 4 sides that you only see 3. So it's tetrahedron. And the way this works is this is the building block for one sheet of a portion of a clay mineral. And these tetrahedrons, they actually come together and they share oxygen atoms and they form sheets or layers. So they form a flat sheet. And you're going to see this time and time again in the upcoming slides. Okay. But the basic building block, one of them is called the silica tetrahedron. And it's called that because silicon or silica, it's silicon, actually fits perfectly in the center between these 4 oxygen atoms. It fits like a glove. It's so the atom itself isn't too big so the structure explodes, and it's not so small that the structure collapses in on itself. It fits just perfect, and it makes this tetrahedron. The other building block for clay minerals is something called the aluminum octahedron. And octa means 6, so there's 6 sides to this, and it's really hard to see in this. It's probably hard to see in this picture, but there's 6 sides. And at the center is aluminum, surrounded by 6 oxygens. Again, just like silicon in the tetrahedron, the aluminum fits perfectly in that space. It's not too big so the structure explodes. It's not too small so the structure collapses in on itself. And this basic building block ends up forming sheets, and we call these octahedral sheets. And so this is how clays are comprised, and you'll learn about this in the next several slides. They're comprised of different formations of tetrahedral to octahedral sheets. Okay, and you learn about this probably in an intro. You should have learned this in an introductory soil science class. Okay, so let me share with you some pictures here. These are also in your notes. So the types of clays that we have in soils across the globe are either 1-to-1. We typically call them 1-to-1, or we typically call them 2-to-1. And then there's a few exceptions that we're not going to talk about in this class. And you probably learned about 2-to-1-to-1, some oddball types of clays out there that are not dominant in most soils. So in this class, we're going to keep this simple. We're going to talk about 1-to-1 type clays and 2-to-1 type clays. So here is an example of a 1-to-1 type clay. The 1-to-1 type of clay is where the silica tetrahedral sheet and the aluminum octahedral sheet combine to form a layer, right? And when we say 1-to-1, that means that there's one layer of a silica tetrahedral sheet, basically bound to one layer of an aluminum octahedral sheet. So an example of this is a type of clay called kaolinite. And it looks like this picture that you have in your notes and you see on the slide here. You have a tetrahedral sheet. Can you see this? Hopefully you can see this. Here's the tetrahedron, right? And it's a sheet of tetrahedrons. And they share oxygen atoms with the aluminum octahedral sheet. This this um, this mineral or this sheet repeats itself, right? So this is one layer. You can't see this with your naked eye. It's at the atomic level. But what happens in these types of clays is this. Let me share with you the next slide. So here's a better example. And hopefully you can see the tetrahedral sheet and the octahedral sheet where my arrows are pointing. And then these layers stack on top of one another. So here's another layer, tetrahedral, octahedral. And then at the very bottom of the screen, there's another tetrahedral sheet and an octahedral sheet, and they stack upon one another. And it takes, I'm just going to take a rough guess here. It takes maybe 100 of these sheets stacked upon one another for you to actually see what you see in the scanning electron microscope picture in the top left-hand corner. When you can actually see these layers, and of course, this is magnified it's magnified quite a bit. I can't see exactly what this is, say 4 micrometers. I mean, this is a very, very small particle, but you can see it in an electron microscope. But each one of these layers that you can see in the microscope is about 100, roughly, of these types of aluminum tetrahedral to, I'm sorry, silica tetrahedral to aluminum octahedral sheets stacked on top of one another. We're going to come back to a concept on this slide in a few minutes, but I want to just share it with you so I don't forget. So these sheets are held together. So you see the space in between these sheets, right? You see the spaces in between these sheets. These sheets are held together via hydrogen bonds. And I don't know if you remember any of this from chemistry class. I always got to go back to my notes and think about hydrogen bonds and other bonds, but hydrogen bonds are strong bonds and they're almost impossible to break. So these sheets, even though it looks like there's a space in between here, there really is no space. They're held together tightly, FYI. And that plays an important role for cation exchange capacity that we're going to talk about in a few minutes. So this is a 1-to-1 type clay. One layer of a tetrahedral sheet to a one layer of octahedral sheet stacked upon itself over and over again. Make sense? Okay. So let's talk about 2-to-1 type clays. And 2-to-1 type clays, again, are a combination of tetrahedral and octahedral sheets. But in this case, there's 2 silica tetrahedral sheets to 1 aluminum octahedral sheet. And that's in each layer. And those layers stack upon one another. And so a typical clay example that we could use would be called illite or montmorillonite, or maybe you've heard the term smectite. These are all 2-to-1 type clays, and we have lots of these in Colorado. In this picture that you see on the slide, and you have this one in your notes, hopefully you can see there's a tetrahedral sheet down at the bottom of the picture, and there's actually one at the very top as well. And sandwiched in between is the octahedral sheet. That might be a little bit harder for you to see, but the tetrahedral sheets you can see easily. I would hope so. Okay, so you have a silica tetrahedral sheet. Sandwiched in between is an aluminum octahedral sheet, and then at the very bottom is another tetrahedral sheet. And this is the basic building block of a 2-to-1 type clay. Let me show you a picture that was similar to a picture you just saw for the 1-to-1. Here's a 2-to-1, right? So let's just don't worry about the pictures and the text on the right-hand side yet. Look at what you're seeing here. What you're seeing in these sheets that are stacked upon one another is at the very top and the bottom of each one of these individual sheets, we have a sheet of tetrahedrons, and sandwiched in between is the octahedral sheet. And then it repeats itself, tetrahedron, octahedron, tetrahedron, and it repeats itself, tetrahedron, octahedron, tetrahedron. And these stack upon themselves. And the images that you see on the right-hand side of the screen are, first of all, a comparison between kaolinite, where my mouse is. This is kaolinite. It's highly structured, typically stacked like this. And or for some reason, this reminds me of when I was a kid and the ice cream man used to come down my street and we'd give him $1 for an ice cream cone and he'd make change. And you remember those things on ice cream man's belt and he had the change dispenser? You know this? Yep. That's what that reminds me of. This picture of kaolinite reminds me of like a stack of quarters in the change dispenser on the guy's hip. That's what the kaolinite reminds me of all the time. This has quite a bit of surface area, kaolinite, but smectites they're actually crystalline in structure, but when you look at them, they look like a giant blob. And if you get up close, that's what's shown in the very bottom picture. This is some sort of smectite. It's a 2-to-1 type clay. It is structured, but it looks completely different than kaolinite, right? I mean, it's not stacked on one another. There's clay particles all over the place in all sorts of different directions. And what this does is it leads to even greater surface area for reactivity to occur. as compared to kaolinite. And what you see in this bottom picture, you can see the actual smectite particle itself, but that's likely about 100 of these chemical structures stacked upon one another that you see on the center of the screen. So you can't see the individual atoms in a scanning electron microscope, but that's what it would end up being, about 100 of these sheets stacked on top of one another. Okay? So you've got the basic building blocks for clay minerals. And up to this point, let me take a step back. Kaolinites, I told you that the interlayer of kaolinites, there's bonding between each layer via hydrogen bonds. And hydrogen bonds are really strong bonds, are basically impossible to break. In 2-to-1 type clays, what holds these together, and maybe this is on another slide, but what I just want to make sure that I don't forget to tell you this. Not that it's important, I'm not going to test you on this, but what holds these sheets together in this interlayer are van der Waals bonds. And if that jogs your memory, that's great. And if it doesn't, I'll tell you that van der Waals bonds are weak bonds. They're easily broken. And that leads to greater surface area in 2-to-1 type clays, meaning these, we call these interspaces, like where you see these blue circles here. The interspaces, when the soil is wet, the interspace can expand and water can get in to the interspace and other cations can move in with the water into the interspace, and it can act and interact with the sheets themselves to increase cation exchange capacity, right? So you probably, I would hope, have heard of shrink swell soils. We have plenty of them in Colorado and in the Western US. They typically comprise of 2-to-1 type clays, typically smectites. In fact, the old Hughes Stadium was built on smectitic soils, shrink swell, lots of cracking of foundations. That's one reason why Hughes was so troublesome over the years, if you know anything about Hughes, because the foundation was cracking because of shrink swell conditions, because of clays like this, with water moving into the interlayer and causing the clays to swell up and crack foundations. Fun, all right? So up to this point, you've learned about the basic building blocks, and you've learned about what 1-to-1 and 2-to-1 type clays look like. But we haven't talked about anything related to cation exchange capacity yet. So how do these compounds actually have negative charge? How does negative charge come about on these compounds or these clays? Let's talk about that next. So there's two ways by which soils or organic matter become negatively charged. So let's talk about the first one. The first method by which soils become negatively charged is called isomorphic substitution. An isomorphic substitution, you'll see this first. Let's talk about what's in red. If you break down the word isomorphic or isomorph, iso means similar and morph means shape or size. So it means similar size or similar shape. That's what this really means. And so the premise behind this is when, and if you look at the example I have on the screen here, when you have an element that's the similar size or similar shape to what element is present initially in the aluminum tetrahedron or the silica octahedron, we'll talk about that next. I'm sorry, the aluminum octahedron. So in this case, we're talking about a substitution of aluminum for silicon in the aluminum octahedron. And these ions are basically the same size, right? So this is what happens when soils weather. When soils start weathering, you get an abundance of other elements in the soil solution that just so happen to be the same size ion as what's present initially in the tetrahedron sheet. or tetrahedron. And aluminum can kick silicon out. And so you see it over here on the right-hand side, where aluminum replaces silicon. And if you look at the basic building block here, then this is a little deceiving because the oxygens are actually shared by other, other compounds that comprise this sheet. But basically, when you start with what you see on the left-hand side, this initial starting point has no charge. There's no charge on it. All the positive charges are satisfied by the negative charges from oxygen. And then these oxygen atoms are shared by other, initially silicon atoms. This structure has no charge. And when you replace a +4 with a +3 charge due to weathering, what happens? You lose a positive charge, right? You start with a +4, and now you have a +3, like you see on the right-hand side here. You lose a positive charge. Another way of thinking of this is you gain a negative charge. This is how a soil becomes negatively charged. And what does this result in? This sort of substitution results in the creation of a negative charge, and that negative charge is actually distributed across the surface of the clay surface. All right, it's not really localized. It's distributed across the entire clay. And this happens often, at least in 2-to-1 type clays. And we'll talk about this in a few minutes. Okay, let me show you another example. Here's another example. It's not as pretty as the last one, but this is an example of negative charge that arises from isomorphic substitution. So the replacement of an original ion with something that's the same size, but a different charge. And so what we typically see in the tetrahedral sheets is aluminum kicks silicon out. And you start with a +4, now you're at a +3. You lose a positive charge, i.e. you gain a negative charge. And then in the tetrahedral sheet, this typically starts, actually not typically, it always starts with aluminum in the center, and due to weathering of soils and the buildup of other ions in the soil solution, for example, in this case, magnesium is basically the same size and shape as aluminum, but it has a lower charge. So in the octahedral, we lose a positive charge, or another way of thinking of this is we gain a negative charge. Make sense? I hope. Okay. So what does this result in? This results in 3 different things. It results in Madison, you have a question? Let me go back.
Oh,
Go ahead.
yeah, I did. I was just curious, how does like pH affect the isomorphic substitution? So I don't know if we were talking about aluminum accumulates in like high or low pH soil. Does that have anything to do with this? I was just curious.
That's a good lead in to letter C on this slide. I appreciate that.
Okay.
I owe you $50.
No, that's okay.
Yeah, okay, thanks. So this is what happens, and this, I'll get to the point that Madison just brought up in letter C here. So when this isomorphic substitution occurs, it creates permanent charge or permanent negative charge. I can tell you that this isomorphic substitution predominantly occurs in 2-to-1 type clays, just because there's more places for isomorphic substitution to occur, and because the interlayer in clays can expand with water. And when water moves into the interlayers in 2-to-1 type clays, it can carry positive charges into the interlayer that can act and interact with the tetrahedral sheets and the octahedral sheets to a greater extent than in 1-to-1 type clays that don't have the interlayer that expands and contracts. So isomorphic substitution predominantly occurs in 2-to-1 type clays. It does happen in 1-to-1 type clays, but predominantly in 2-to-1. And when this happens, and Madison, I'm talking, sort of directly to you, but to everyone, the charge is permanent and it's not at all affected by pH. The negative charge due to isomorphic substitution would be the same if you were at pH 4 in a soil versus pH 9 in a soil. You would still have negative charge due to isomorphic substitution. I can tell you that what's sorbed onto the outside of the clay is definitely going to be different at pH 4 versus pH 8 or 9. But the charge on the soil itself or the clay itself is not going to be affected by pH. So this is one way in which soils become negatively charged. Okay, isomorphic substitution. But there's actually another way in which soils become negatively charged. And this is also a good lead into Madison's question. So soils also can become negatively charged because of the edges of minerals, the edges of clays, and the outside edges of organic matter that are sticking out into the soil solution. And those areas are all affected by pH. So here's an example of something that we call pH dependent charge. So when I ask students, how do soils become negatively charged? You would say, okay, number one, isomorphic substitution, and number two, pH dependent charge. And then you should be able to tell me what isomorphic substitution is. You just relearned it. And then you should tell me how pH dependent charge arises. And we're going to talk about that now. So this is the other way in which soils become negatively charged based on pH. This occurs always. If it's going to occur anywhere, it's going to occur at the edges always of clay minerals or soil minerals or clays or clay minerals. And at the edges of all these minerals or clays, the edges that are sort of sticking out. So we're not talking about the inside the interlayer. We're talking about the edge. At the edges, these are affected by pH. And so this diagram here shows you how pH would affect the charge at the edge of a mineral or clay. And when a soil is extremely acidic, there's a lot of free hydrogens in the soil, and the hydrogens stack up and combine with these oxygen atoms that are sticking out on the edge of clay minerals or other minerals. And this is actually water, right? H2O, but it's structural water. It's actually part of the mineral structure at the edge. And then if you raise pH, one of those hydrogens can get kicked off. And now at low pH, you have a positive charge, actually, believe it or not. At relatively neutral pH, you have no charge. And if you raise the pH even more, another hydrogen gets kicked off. It's not written perfect on this screen, but another hydrogen gets kicked off. And now oxygen at the edge of that mineral has a negative charge. And this is how pH-dependent charge works. The name pH-dependent charge is the definition. The negative charge is derived based on pH, right? So at very high pH, the soil is negatively charged. At near neutral pH, the soil, and I'm keeping this simple, but at relatively neutral pH, the soil has no charge or no pH-dependent charge. And under extreme acidic conditions, the soil has a pH-dependent charge that's actually positive. It's really goofy, but it's positive. Okay, so this is soil minerals or clays, but it also comes from organic matter. And if you look at a picture of organic matter, the same reactions basically happen at the edges of organic matter where you have these functional groups sticking out into the soil solution. So the negative charge that comes from pH-dependent charge in organic materials is simply from the dissociation of the hydrogen from either carboxylic groups or phenolic groups that are sticking out from the edge of organic material into the soil solution, right? So here's a picture, it's a rough picture, of a soil at a low pH. And here's a carboxyl group, and here's another carboxyl group, and here's a phenolic group or an alcoholic group. And they're at low pH, there's plenty of hydrogens floating around in the soil solution, and the oxygen is satisfied by those protons. And this has no charge. And if you raise the pH, you lose those hydrogen ions from those reactive sites, and the oxygens now have a negative charge. So this is where pH-dependent charge comes from. It comes from raising pH above a point where the hydrogen ions that are initially stuck on either the edges of clays, the edges of minerals, or the edges of organic functional groups sticking out in the soil solution, those hydrogen ions are kicked off, and the pH-dependent charge comes about. Okay, so in soils, you have two charges, permanent charge and dependent charge. Makes sense? Hopefully? Okay. We could spend an entire semester talking about this one slide. And we are not going to do that, all right? So this gives you the basic tools that you need to understand how pH dependent charge and isomorphic substitution work to lead to a negative charge in soils. And that negative charge holds positive charges like magnesium, calcium, iron, zinc, manganese, copper, most of the nutrients that are necessary for plant growth. Not all of them, but most of them. So there's one other slide here. I think this is, yeah, this is the last slide I want to talk about charge. And on the last slide, or the last two slides, talked about that sometimes soils can actually be positively charged. Now, this is something you can listen to me now, like hold one ear, let this information go in one ear, and then when I'm done talking about positively charged soils, you take your hand off the ear and let it flow out of the other ear, okay? So soils can actually become positively charged. It's based on pH-dependent charge. And sometimes soils have something called anion exchange capacity. More often than not, probably 99% of the time, we talk about cation exchange capacity. So soils are negatively charged and they can hold on to cations or positive charges. Every once in a while, and this is the crazy thing about soils, much like anything you study, is that there's always exceptions to the rule. And every once in a while, a soil can become positively charged. And that's because of acidic conditions and hydrogen ions being loaded onto the edges of clay minerals or other minerals, or maybe even sometimes on the edges of exposed carboxyl groups. And what you see is what you see in this picture here. And let's pick on this red line or this red curve here for a second. And what this shows you is as the pH on the x-axis drops and the soil becomes more and more acidic, a positive charge can develop. And that's because of extra hydrogen ions stuck on the outside of those phases where you have, essentially structural water and a positive charge arises. So if you go back actually in your notes, if you have your notes in front of you, if you go to the very top of your notes, it shows you a picture of pH dependent charge where the soil becomes positively charged. Right, and that's expressed on this red curve. The crazy thing about this red curve is that it happens, but the beauty of this red curve in this diagram is that plants hate living at below pH 5 or so. So you're hardly ever going to see this occur in soils. Okay, so now you can take your hand off your ear and let the anion exchange capacity information, leak out of that ear and into oblivion. But you should know that, it's interesting to know that soils can become positively charged. And the whole premise behind this class is to not have soils at pH 4 or pH 5, to have them around 6 to 6.5 or so the nutrient availability is greater. So you wouldn't be working with soils that are positively charged anyway, because of this fact of this class. So here's some take-home messages. Okay. In terms of pH-dependent charge, number one, the cation exchange capacity increases with increasing pH. Right, and that's because of the pH-dependent charge. Point number 2, this is the point you can sort of disregard, but anion exchange capacity decreases with increasing pH. You see that in the red curve as you go from acidic to basic conditions. And then the caveat here for everything I just taught you this morning with respect to pH-dependent charge is that pH-dependent charge really depends on specific clay minerals that are present and the type and amount of organic matter that's present. And I didn't teach you, and I'm not going to teach you this, but hydrogen ions come off of the edges of clay minerals or organic moieties at different pH values. It's not just all or none, right? And so when I said on a previous slide, we could talk about this one particular slide for a whole semester, I'm not kidding. Like each organic functional group loses a proton at a different pH value, and it's complex. So we're just going to keep it simple, right? The simple fashion that we're going to teach you in this class is as pH goes up, pH dependent charge goes up. That's because hydrogen ions are kicked off and there's more negative sites that are created. I hope all this makes sense, and I made this as simple as I could. Are there any questions up to this point? No? Okay. Awesome. So let's do this. I want to focus attention on some different types of clay minerals because you're going to run into these. If you ever work with soils and you're wondering, well, how come my soil just keeps leaking calcium, for example? Oh, that's right. I'm working in South Carolina, and it's a 1-to-1 type clay, and I have a lot of leaching going on. I mean, these are some of the basic concepts that you're going to learn about these types of clays that you could apply anywhere in the world. So we're going to focus attention on 1-to-1 type clays, and then we're going to focus attention on 2-to-1 type clay minerals. So let's talk about 1-to-1 type clay minerals specifically. So these are minerals, you just learned about this, or clay minerals that have one layer of a silica tetrahedral sheet stuck together with one aluminum octahedral sheet, and then they stack on top of one another, right? These sheets stack on top of one another. So that's letter A, one layer of tetrahedra and octahedral sheets stacked on top of one another. In these clays, there's very little isomorphic substitution. And there's a reason for that, because the layer in between, like in this diagram that's in front of you or in your notes, it says hydrogen bonding between basal planes. The bonds that hold these sheets together in this interlayer, they're strong bonds, and they're hard, if not impossible, to break. So the only way you can have isomorphic substitution is pretty much on the edges of these clay minerals, or not on the edges, but the elements that are near the edges of the clay minerals. Way in the center, in the interlayer, it is going to be impossible to have isomorphic substitution way inside here because there's no shrink swell and there's no water moving into these interlayers because of the strong bond. So isomorphic substitution is relatively low. It does happen, but it's relatively low. And in 1-to-1 type clays, the charge is dominated by pH dependent charge because that occurs on the edges. Oops, sorry about that. Because pH dependent charge occurs on the very edges of these clay minerals, right? The edges of the clay minerals lose hydrogen, and then the oxygen is left holding a negative charge. That derives pH dependent charge. These soils typically have a low cation exchange capacity, and you'll see what this means in a minute. Low is less than 10 milliequivalents per 100 grams. It's a goofy unit that should make sense to you after we're done with this unit, right? But that's the unit we use to express CEC, milliequivalents per 100 grams, and 10 is a low value. 1-to-1 type clays are typically found in weathered soils. So when I think of weathered soils, I think of like the southeastern US. Certainly not in Colorado. And when you look at CEC overall, it could be 50% of the CEC is based on pH dependent charge, and that's huge. Okay. So that's 1-to-1. Let's talk about 2-to-1 type clays. Now these 2-to-1 type clays, in your notes it says montmorillonite, smectite. You could even list illite. I put that on this slide in the center up there. They're all 2-to-1 type clays, right? And so that means there's 2 tetrahedral sheets to 1 octahedral sheet. Like you see in the picture in your notes and on the screen, here's a tetrahedral sheet. Here's another tetrahedral sheet, and sandwiched in between is an octahedral sheet. And this structure stacks on top of it stacks on top of itself. Okay. And these clays sometimes have expansion and contraction or shrink swell capabilities. And that's because, where's my arrow? Here in the interlayer, the bond or the bonds that hold each one of these layers of sheets together, you don't see it here, but the bond is actually a van der Waals bond, right? And van der Waals bonds are weak bonds. And if let me tell you a little bit more about van der Waals bonds. So van der Waals bonds arise from electron spin, so electrons floating around the outside of atoms. And every once in a while, more electrons are on one side of the atom versus another side. And that creates polarity. And that's basically a van der Waals bond. They're weak bonds. They come and go rather quickly. They hold these sheets together, but in the interlayer, those bonds are easily broken. And when the bonds are broken, water can move into the interlayer and it can carry ions, like in this case, that's sodium. And sodium can get into the interlayer and push these particles apart. So can water. So they have shrink swell capacity. And the other interesting part about that shrink swell is when ions move into the interlayer, now they can act and interact with the ions that are in the center of these tetrahedrons or octahedrons. And those ions in the interlayer can replace aluminum or silicon. That creates negative charge. That's isomorphic substitution. And so the CEC on these types of clays comes from pretty much isomorphic substitution, dominated by isomorphic substitution, but also on the edges of the clays, broken edges or just the edges of clays. That's where pH dependent charge would come from. So these soils or these clays in terms of CEC, they're really high in terms of cation exchange capacity, 80 to maybe 120 milliequivalents per 100 grams. That's different than kaolinite, which is about 10. And these types of clays, only about 5 to 10% of the CEC comes from pH dependent charge. And that's because there's all this shrink swell. There's all this shrink swell going on in the interlayer and ions interacting with the initial ions in the tetrahedrons and the octahedrons. And you have a replacement. Okay. So you know something about the dominant clays, 1-to-1s and 2-to-1s. 1-to-1s, maybe 50% of the negative charge comes from pH dependent charge, the other 50 from isomorphic substitution. And then you have 2-to-1 type clays, 90 to 95% comes from isomorphic substitution, 5 to 10% comes from pH dependent charge. So where does all this happen? It happens all over the place in soils, right? So you already learned about this picture. We talked about this already. We talked about ion exchange occurring on clay surfaces, or clay edges. It occurs on actually organic matter. That should have been letter B, but the edges of organic matter. It actually occurs on inorganic compounds or mineral phases, like this picture here on the right-hand side of limestone. At the very edge of limestone, you can have actually negative charges that are derived right at the edge that can hold positive charges. This happens on mineral phases all the time. And then it happens at roots. Ion exchange happens on root surfaces. But dominantly, when we talk about this in this class or outside of this class, and we talk about cation exchange capacity specifically, we're talking about clay surfaces or clay minerals and organic matter. Okay, so what I want to do is I want to share with you some more data of the interpretation of minerals and soil textures, to be honest with you. So let's take a look here. We know that CEC is influenced by clay type and organic matter. And if you were to collect clays, the different types of clays and organic matter and measure cation exchange capacity, and these are rough values, but they give you a good generalization of what you might find. So you have this table in your notes. Kaolinites typically have, it says 8 milliequivalents per 100 grams. Yeah, 8, 10, it's pretty low. Micas, maybe about 30. Montmorillonite, this is a 2-to-1 type clay. Vermiculite's a 2-to-1 type clay. These have like 80 to 150 milliequivalents per 100 grams of charge, negative charge. And organic matter is really, really high. And so if you knew what types of clays and how much of that clay you had in the soil, you could probably determine CEC. You could just guesstimate it. Let's look at this a different way. Another way of looking at this is that CEC is actually influenced by soil texture. So if you know something about soil texture, you probably know something about cation exchange capacity. So this is, when I teach this class, this is the puzzle I like to talk about, right? So you could, to be honest with you, you can actually determine cation exchange capacity in a lab doing some sorption experiments and desorption experiments with different ions. You could do that. That's how most testing labs perform this. But you could determine CEC based on the amount of clays present, the types of clays that are present. You could determine all of that. Or you could determine CEC or estimate CEC based on texture, like you see in front of you. So sands that are light or dark colored have relatively low CECs, like 2 to 4 versus 8 to 16 milliequivalents per 100 grams. And then as the soil becomes finer and finer, as you go from a loam to a silt loam to a clay, the CECs increase. And that's simply because there's more clays present, right? There's more clay present in a clay or a clay loam than a sand. So this has everything to do with that one of those first slides in this unit where we talked about surface area. There's simply more surface area for reactivity to occur in clays and clay loams, and so CEC is higher. And then when we look at organic soils, and these soils are soils that have greater than 20% organic matter present, and more often than not, we don't work with these in most arable soils that we use for raising crops, but some people do. And those CECs are relatively high because of pH-dependent charge, because of organic compounds present and those organic moieties with carboxyl and phenolic and alcohol groups sticking out of the sides into the soil solution. Okay. So this is the puzzle. This is the puzzle I'm trying to teach you, that you can derive CEC from a known soil texture, or you could probably go backwards. And if somebody told you what the CEC of a soil was, and you went to a chart like this, or if you memorize this chart, you could probably guesstimate what the soil texture is. And you probably would be pretty close. So what I want to do is I want to share with you some real world examples. And these aren't in your notes, so you can just kind of sit back and relax and learn something here. So let me share with you this document. This is this is relatively old. I should get an updated one. This is from 2007, but this is a soils report. And if you've never seen a soils report, typically looks like this. It comes from a laboratory, typically has a name on a laboratory, has probably the person's name or entity that they work with somewhere on the sheet. And then you'll see lab number and field identification, blah, 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 blah. These all correspond to soils that were pulled out of, I don't know what tall and short mean. And then you could see soil depth. And then you see a bunch of data on this. And what I want to focus on is this cation exchange capacity column. And if I zoom in on this, let's zoom in on this. On the cation exchange capacity column and the units, it's hard to read, but it's milliequivalents per 100 grams. That's the unit by which most people express CEC. And we're going to learn what that means either today, and we'll probably get to it today. All right. But let's just take a look at the numbers themselves. So if you see these numbers, 25.6, 25.9, 29, 28, I mean, they float around like between 25 and 30 centimoles a charge. I'm sorry, milliequivalents per 100 grams. What's the texture? So if you went if you have your notes open in front of you, or you looked on the screen, I just posted this, right? So 25 to 30 puts you either, it most likely puts you in the clay and clay loams category. Now, if I go back a slide, let me go back one. On this soil test, if you look at it, there's no place where soil texture is identified. But if it was identified on this sheet, I would hope that it would say a clay or a clay loam. And it probably would, to be honest with you. Okay. We're going to come back to that actual real world example either today or next week, Tuesday. So I want to switch gears here, and this unit or units of expressing CEC is a little goofy, right? Milliequivalents per 100 grams. What the heck is that, right? I mean, what is that? What this is that it's an expression of the number of negative charges in a soil. And the unit of negative charge is milliequivalent. And then we just put it on a 100-gram basis, right? It's a goofy unit. Like, you can't weigh a milliequivalent on a balance. You can't, right? You usually weigh grams, kilograms, or ounces or pounds on a balance. You can't weigh milliequivalents, but we can determine it, right? And it's simply a unit of charge. The units, like I said, the units that most labs typically use are milliequivalents per 100 grams. If you are a geeky scientist like myself, we use the SI units, which is centimoles of charge per kilogram. And I can guarantee you, when we talk about CEC, either today or on Monday, when we finish this unit, I'm likely to say centimoles of charge per kilogram because I think like that. But the units that you will always use as like a layperson or non-scientist from a testing lab will be milliequivalents per 100 grams. And the beauty of these two types of units is that they equal one another, basically. Okay. It's a 1-to-1, which makes it really nice as a scientist. So what is this? Milliequivalents per 100 grams is a unit of charge. And this unit of charge deals with something called equivalent weights. And we talked about equivalent weights really, really simply when we were talking about liming acid soils, right? We're talking about the equivalent weight of calcium carbonate being 50, right? And that was the molecular weight divided by the number of hydrogen ions that were kicked off exchange sites by calcium. And calcium was a +2 charge, and it kicks off 2 hydrogens from exchange sites. So the concept there is similar to what I'm going to teach you here in terms of equivalent weights. So there's some information here that I'm gonna skip. It's in your notes. You feel free to write down these first 2 lines if you want to, but I like the last line here. Equivalent weight is simply the atomic weight of an ion divided by the charge of that ion. Simple. Okay. And before we get into all these details, the reason why we express charge or cation exchange capacity in milliequivalents per 100 grams or on a charge basis is because a soil can have 100 negative charges. Right, I'll make up an example here. A soil can have 100 negative charges, and those 100 negative charges can be satisfied by 100 hydrogen ions. Those 100 negative charges can be satisfied by 50 calcium ions, And those 100 negative charges could be satisfied by 33 1/3 aluminum ions, right? And that's because each one of those ions is either +1, it's +2, or it's +3. And so when we express cation exchange capacity on a charge basis, we don't express it on the number of cations it can hold, because the number of cations that a soil can hold depends on the charge of the cation. So we express cation exchange capacity on a charge basis, and that charge is milliequivalents per 100 grams, because that tells us basically how many negative charges are present in a soil. Okay. And then this calculation of equivalent weight, of taking the atomic weight divided by the charge, what that does is it makes all ions, regardless of their charge, equivalent to one another. So if you took potassium, which has a +1 charge, you divide it by the charge, and then you take calcium and divide it by the charge, which is 2, and you take aluminum and divide it by the charge, which is 3. It makes the amount of negative sites that'll be satisfied by each one of those ions equal to one another. Okay, so this is, if this doesn't make sense now, it will, I hope, after we're done talking about this section in this unit. Okay, so where are we going here? So this section down here in this soils report is the amount of charge per 100 grams that the soil, each one of these soils has. And they just so all happen to be about the same because they're all taken probably from a very similar site or location. Okay. I hope this all makes sense to you when we finish this section, because equivalent weights is a little goofy. So I want to talk about how to calculate this, right? So we calculate equivalent weights when we determine CEC. So each ion is equivalent to one another simply by taking the molecular weight divided by the charge of that ion. So this is what we do when we determine CEC. All right, so when we have univalent ions, like potassium, sodium, ammonium, we take the atomic weight divided by the charge. Right, so for example, potassium, if you went to the periodic table, atomic weight is 39, and it has a +1 charge. So 39 divided by 1 equals the equivalent weight. And that's expressed, and it's goofy, but it's expressed here, 39 grams per equivalent. Right, and it shows you how I got to that. And I'm going to try to keep this relatively simple. And in fact, if you don't have the units correct here, it's 39. If you have sodium, if you go to the periodic table, is 23. It has a +1 charge, so 23 divided by 1 essentially is 23. That's its equivalent weight. We do the same thing with divalent cations. Same approach. You take the atomic weight divided by the valence. So in this case, there's 2 examples here. One's calcium. And calcium, if you go to the periodic table, has an atomic weight of 40. Calcium has a +2 charge, so 40 divided by 2 equals 20. I'm sorry, I wrote this out in longhand for those of you that wanted to see it, but it's basically 40 divided by 2 equals 20. That's the equivalent weight of calcium. Magnesium's different, right? Because it has a different atomic weight. The atomic weight of magnesium is 24, but it has a +2 charge. So 24 divided by 2 is 12, and that's the equivalent weight of magnesium. Then we do the same thing for trivalent cations like aluminum. You go to the periodic table, aluminum has an atomic weight of 27, and aluminum has a charge of 3. So 27 divided by 3 equals 9. That's the equivalent weight of aluminum. And we do this because we need to put each one of these types of cations that may be stuck on the outside of exchange sites on an equivalent basis, right? So if you were to take these, imagine all these cations were stuck on the outside of a clay, and you strip these cations off and put them into a solution, and then measure them, you would come up with the total amount of aluminum, the total amount of calcium, and the total amount of potassium present. And if you added all those together and said my CEC is a number based on just the total amount of these ions present, you would be wrong. And that's because aluminum, well, that's because like for example, potassium is going to satisfy one negative charge on a cation exchange site. So you would measure one potassium, and you would know that that would be associated with one negative site. But if you measured one calcium ion and you said, oh, that equals one negative site, you would be wrong. That equals two negative sites, right? Because of the +2 charge. And if there was one aluminum stuck on the outside of a clay particle and you measured that, you would say, oh, that's one negative site because I measured one cation. No, the cation has a +3 charge. So aluminum is satisfying three negative charges on the exchange sites. So in order to make all these equivalent to one another, to determine cation exchange capacity, we have to go through this calculation. And testing labs do this all the time. And if you worked in my lab and you were to determine CEC, you would do this in my lab, right? You would measure all these ions that come off of the exchange sites, keep this general, and then you would go through this calculation that you see on this screen to determine the equivalent weight of each one of those cations, and then you would add those up to determine CEC. Okay? It's a weird concept. So let me share with you this example again, right? So this example from this lab, Olson's lab, Olson Agricultural Laboratory, it's in Nebraska. So this very first circle, or this very first soil where I have this box, it has a CEC of 25.6 milliequivalents per 100 grams. That's the CEC. And how did they come up with this number? It's not magic. What they did was they determined the amount of potassium, calcium, magnesium, and sodium on the soil, on the exchange sites. And I'll tell you a little bit more about how they did this, and I'll keep this simple. So you see this term, it says ammonium, blah, blah, blah. It's ammonium oxalate extraction. And what we do in a lab is we flood a soil with ammonium ions. And those ammonium ions, if you place enough of them in solution, they kick the basic cations. They kick calcium, potassium, magnesium, and sodium off exchange sites so we can measure them. And that's what this lab did. They kicked potassium, calcium, magnesium, and sodium off of cation exchange sites, and then they measured those different cations. And you can see the numbers here, 902, 3030, 703, and 524, and this is all in ppm. That's milligrams per kilogram. That's what parts per million means in this context. Okay? So the units over here on the left side of this page that you would act like you would get a page like this from a soil testing lab. How did they go from this box on the left to this box on the right? They went from the box on the left to the box on the right by converting all these concentrations in ppm or milligrams per kilogram. They converted them to milliequivalents per 100 grams based on the calculations I just showed you on the previous slide. So let's do it. This is what the soil testing lab did. This is right from that sheet from the previous slide. This is in your notes, right? A soil's extracted and it had these cations present on it. This is, again, directly from the last slide. 3,030 milligrams of calcium per kilogram, 703 milligrams per kilogram of magnesium, 902 milligrams of potassium per kilogram, and 524 milligrams of sodium. So what's the CEC? To know or to determine the CEC, you have to know what the atomic weights are, go to the periodic table, And then you need to know what the equivalent weight is of each one of these cations. Okay. And what we do, that middle step of knowing what the equivalent weight is what's written here. We need to convert the above concentrations to milliequivalents per 100 grams, right? And how do we do this? Let me show you how to do this. And in the past, in this class, I used to show the longhand version of this, and I could see that all of my students would glaze over. So I'm going to give you the shortcut. This is the shortcut. And if you ever want to see the longhand version, I'm happy to share it with you. But I want to show you the shortcut. So this is the shortcut. The shortcut's this. You take the milligrams of any cation per kilogram. That was the left-hand side of that document from the testing lab. And you multiply that value by the cation valence, the charge, divided by the atomic weight. And then you take that whole number and divide it by 10. And that's going to give you milliequivalents per 100 grams. And in this equation, in the denominator, that 10 is a shortcut for the conversion from the units in the numerator to milliequivalents per 100 grams, right? If you ever want to see the longhand version, I can write it out and I can take a picture and email it to you, or we can go through it online. But that's the simple conversion, this simple equation, okay? And so what I want to do is I don't want you to write any of this down, okay? So because we're almost at time, and this is probably going to blow your mind on a Thursday morning, that we're going to start here. Actually, we'll probably start on the previous slide on Tuesday next week. But what this shows you, just as a prelude, is the conversion based on that shortcut at the very top of the screen, where we take the values that came from the soil testing lab. And this is what the soil testing lab did. They took all these concentrations of these elements and they converted them to milliequivalents per 100 grams based on the shortcut above. And then they added all these values in this last column to come up with the CEC. So I'm going to share this with you next week, Tuesday. So it's fresh in your mind in order to determine or to do the calculation. Okay. So if you're going to write this down, that's fine. Now I'll leave it up on the screen, but I'm going to revisit this because this is like a little deep right now, and we're not going to finish in 2 minutes. Okay. So why don't I stop here? Are there any questions on up to this point for this unit? None? Wow. All right. So
There's
you either
no questions. Can Cassidy make an announcement real quick?
go ahead, Cassidy.
Just a reminder that for the people that are in my lab will be in W003 today, and we will be working with soils. So wear your proper attire, please.
Awesome. Thank you. All right, everyone. Well, thanks for being here today, and have a great rest of your day. Have a great weekend. See ya.
Have a good weekend, Jim.
Yeah,
you.
you
Thank you,
too.
Jim.
See you, Jacob. See you, everybody.
Thank you.
Thank you. Thanks, Babatunda.